Compound interest, this is section 5.1. For an original principal of money P, the formula S equals P times 1 plus R to the power of n gives the compound or accumulated amount S at the end of n interest periods at the periodic rate of R equals APR over big N. What is APR? It's the annual percentage rate, also called the nominal rate. So you can't just write little n per year. You need to define a new quantity for that. Obviously, the units are significant here. This is not just the number of interest periods, as is little n. It's the number of interest periods per year. So you have to pay attention to those units. Paying attention to units of physical quantities is very important, especially when you're finding yourself having to plug these quantities into a formula. You have to know how the units cancel out. Here, if you look at my remarks, the first remark shows you just that. Little n is how we can define little n to be the time, t in years, times big N, the number of interest periods per year. So you'll see that if time t is in years and big N is per year, then the years cancel out, giving you just a number. So without any units, significant units. So this is n interest periods. So you see how that works. 2. Compound interest is simply S minus P. So when you subtract the original principal of money P from your accumulated amount, that's how you get your compound interest. Okay, so let's look at some sample questions or just some basic examples related to this. Okay, so here's our first example. I also note that it's similar to question number 10 on page 212 of your textbook. It says here, suppose that over a 6-year period, $1,000 accumulated, there's a keyword, accumulated to $1,959. If interest was compounded, there's another keyword, quarterly, what was the nominal rate of interest earned? Round your answer to 2 decimal places. So you'll see here that I solved it for you. We are given P equals $1,000, so that's the principal, and we're told that it has accumulated to 1959. So if it's accumulated to 1959, that means the accumulated amount is S equals $1,959. Then we're told that we're asked to assume that interest was compounded quarterly. So what are we talking about? We're talking about compound interest, but quarterly. Quarterly means that it's every 4 months. It's a quarter of a year. But the point is, the number that we're concerned about is 4. It's a quarter of a year. We're talking about the number 4. It's the number of interest periods per year. That's what we mean. There are 4 interest periods per year. So the nominal rate of interest earned must be APR equals little r times big N. So basically I just rearranged that equation that you had, little r equals APR over N, and we plug everything in, plug the little interest rate r. I did some quick little algebra here. You can rearrange it yourself, plug the relevant quantities in, and you'll see it comes out to the 24th root of 1959, or $1,000. Notice the dollars cancel again over here, and minus 1 times 4, because n equals 4, and comes out to about 0.11, so about 11%. And really, that's how these financial mathematics problems are. It's just a matter of sorting out the quantities you're given, listing them out explicitly. It's really worth doing. You know, not every student would have caught n equals 4 over here. So, you know, you just got to keep your eyes wide open, catch those quantities, and you know, list them out properly. And then once you're sure that you've done that, plug everything into the relevant formula. You may have to rearrange, but you know, that's pretty much high school. Okay, so that's that question. Okay, example 2. So just refer to page 13, number 20 in your textbook. It says, how long will it take for $100 to amount to $1,000 if invested at 6% compounded monthly? Express the answer in years rounded to 2 decimal places. Okay, so here I've presented my solution. I've used logarithms because that makes it easier. You'll see given P equals 100, that's obvious, we're given $100. That's our principal, and it's saying how long will it take for it to amount to $1,000. So again, key word, amount to. That means $1,000 is the accumulated amount S. It says if invested at 6%, so whenever it's talking about percentage, it's talking about most likely annual percentage rate, and yeah, we see that's what it's talking about, investing at some rate compounded monthly. It's talking about APR, so that's 0.06 or 6%. It's easier to convert these percentages to decimals, and it says compounded monthly. So when we're told monthly, you have to think how many interest periods per year does that mean. So if it's every month and there are 12 months in a year, that means that we're talking about 12 interest periods per year. So that's our big N. N equals 12. Thus, plugging everything in once again, $1,000 is equal to $100 times 1 plus 0.06 over 12 all to the power of n, because remember the formula that S equals P times 1 plus R all to the power of n. So you see little r, again, equal to APR over big N. So I'm just plugging everything in. You just have the formulas in front of you, and so yeah, you plug it in, and what does that work out to? 10 equals 1 plus 0.005 all to the power of n. Okay, so how do we break out of this power? That's why we introduce logarithms. So, okay, we added the 1 to 0.005. That's easy enough. How do we get rid of this power to this power of n? So, using logarithms, I can take log of 10 over here. Why do I take log of 10? This was purely strategic, because log, when we omit the subscript, nowadays anyway, it's understood that we're talking about base 10. You know, ln is log to the base e. E is approximately 2.718, and log to the base 10 of 10 cancels and becomes 1, as you see here. So that's why I use that. So when you use logarithms, you can be strategic as possible. If this were, say, the number 3, I would take log to the base 3 of 3 to make it 1, depending on the situation. Most of the time we don't need to do that. We just deal with either common log, as it's called, log to the base 10, or log to the base e, which is ln. Normally we just deal with those two, so don't worry about other bases. But I'm just trying to make a point here that you know, logarithms, we can very strategically eliminate certain constants and make our work a little bit easier here. Anyway, that was just an aside. So in this question, there isn't much going on. Once again, we're just plugging the relevant quantities in the formula, and we're trying to break out of this power of n. Remember, that's our goal. So we take log of 10 on this side, log of the other side. That gives us 1 equal to n log 1.005. So our other motivation, other than breaking this part down, was to bring this power of n down, because we know that when we take log of some, I don't know, quantity x to the power of, say, r, then the result is r log x. We can bring that exponent down. That's what we're trying to do. So that's what we've done here, and we've broken out of it nicely, and so we rearrange for n, and it gives us 12 times t equals 1 over log of 1.005. Punch that in your calculator, and we get t equals 38.47. Okay, so the third example I have here is page 212, number 9. It says, over a 5-year period, a principal amount of $2,000 accumulated to $29.50 in an account in which interest was compounded quarterly. Determine the effective rate of interest rounded to 2 decimal places. Okay, so right away we can see what quantities are popping out. We have principal, we have accumulated amount, we have interest compounded quarterly, so we know what to do with that, define big N, and then determine the effective rate. Well, we take note of the formula for effective rate, which is, let's pull it up here, R sub E is equal to 1 plus R all to the power of big N, not little n, minus 1. if you stick with the notations that I've used in these financial math formulas, then everything should be okay, smooth sailing. I noticed that your textbook unfortunately recycles a lot of notation, so when they're done with one section, they'll move on to the next and reuse some variables. And this is actually very bad practice, because when you're dealing with an application like finance, when you're doing something like physics and you have all these recurring formulas, it is not a good idea to repeat variables for defining new quantities. Once you use a variable, say t, and designate it to represent, say, time, you should really stick to that and not let it equal to something like, I don't know, temperature. So it's just like you need to be consistent with the notation, and there's only 26 letters in the English alphabet. I understand how frustrating that can be, but the point is that we don't want to be confused by recycled notation, and unfortunately your textbook does that, recycles notations. Anyway, so getting back to this question, we need the effective rate formula. So basically, let's take our quantities and plug them in. And if we do that, we have 2,000 times 1 plus r sub e to the power of 5 equals 2950. You see the units cancel out, the dollar signs cancel out. 1 plus re all to the power of 5 is 2950 over 2,000, just rearranging and, having plugged everything in, just simplifying nicely. In the next line, 1 plus re equals the fifth root of 2950 over 2,000, and that leaves us with r sub e, effective rate, equal to fifth root of 2950 over 2,000 minus 1. So this is actually the exact value, but of course it's asking us to determine the effective rate of interest rounded to 2 decimal places. So when it says rounded to 2 decimal places, we see that we're being asked to approximate. That's another important point. When you're doing these types of questions, you have to understand when you're asked to give an exact value versus when you're asked to give an approximation. When it says round to this many decimal places, you're being asked to approximate. So please do not write equals. So in this case, we have RE is approximately equal to 0.0808 or 8.08%. This is the correct answer. But if we write RE equals this, then we're actually incorrect, because that would contradict this line over here. Even if the difference is very small, mathematically we cannot put the equal sign on approximations. That's why we have this symbol, so please do not be afraid to use it. This is the correct one to use. So here, exact value, here, approximation. We've answered the question, and so ends these relatively simple questions in financial mathematics for this section.